Uh, Good afternoon, all. My name is Subhashis. I'm going to present my. First of all, I would like to thanks IEEE Census for giving me this opportunity for presenting my work. The work is entitled on acetone adsorption characteristics of palladium AlGaN heterostructure, which is grown by plasma-assisted MB and its kinetic interpretation at low temperatures. So that the background image is of our institute, which is situated at the lab of MLIs. So I'll go to the. This is the outline of today's presentation. In introduction part, I will cover a little bit about my motivation and what is the use of acetone sensor, and then I will go to the fabrication and characterization part of the material, and then how it applies for the acetone sensing purpose, and then conclusion. So first of in the motivation why sensors, from yesterday you were hearing everything about sensors, why sensors. So I will quickly skip to the next portion. So why 3-nitride? So first of all, Fermi pinning in 3-nitride material systems, there is incomplete Fermi pinning, and because of that we can manipulate the Fermi level shifting by means of changing the carrier concentration when every gas is introduced or it is turned off. And then wide band gap semiconductor, it will give the high temperature stability and a high ruggedness. That means that material system can be useful in the adverse environment, and the inherent polarizability in this material system will give the advantage of very high sensitivity towards the change in the surface state. So these are the mainly objective of this work, to demonstrate the acetone vapor sensing performance of AlGaN heterostructure on silicon 111 and to evaluate the reaction rates and activation energies of adsorption and desorption of acetone. So these are the need for acetone sensor, to name a few among the others: the environmental monitoring and breath tests. So I will go to the material section first. So we have used the molecular beam epitaxy system to grow the different layers of gallium nitride and aluminum gallium nitride with different percentage of aluminum and with the different thickness of the layers. So the beam equivalent pressure was kept in 0.69 for aluminum barrier layer, and it was varied with different layers for the buffer purposes. And we are getting very good graded buffer to strain management and dislocation filtering of the barrier layer of the structure. So now this was the temperature estimation of the growth method. At the 950 degrees Celsius, we are cleaning the wafers, which will give in later slides you can see it will give the best quality of the crystalline quality of the material. So next is this is the read pattern, which will give first. You can see there are 7x7 read pattern. Prominent Kikuchi lines are there, so you can conclude that it is giving the best crystalline quality. And whenever we start growing different materials, it is showing streaky patterns, which will tell us that the single crystalline nature of the material. And in the next slide, you can see the same streaky line of the AlGaN barrier layer, and this streakiness with the barrier layer and the buffer layer will give the high electron concentration in the hetero interface, which will inherently give the sensitivity more. So next, I'll go at HRXD scan results to characterize the material and its quality. So first of all, we have done the symmetric and asymmetric plane scans. From there, we have calculated the we have calculated the molar fraction for different AlGaN layers, and it will say that it will give the distinguishable peaks and good quality crystal have been grown. These are few results which has been calculated from the peak splitting of that ICD curves. So next we have measured the layer thickness by cross-sectional TEM, and we are getting the this much of thickness from the TEM images. And next we'll done the surface characterization by AFM and FSM techniques. So surface roughness has been found to be 1.69 nanometer. With this low surface roughness, good surface quality we are achieving, and from the FESM micrograph, the top surface, we can get some typical surface quality which is good for sensors. So this is basically the sensor structure, that is the schematic structure of, and now this is the resistance versus temperature curve. Whenever we are introducing the acetone vapors with different concentrations, we are getting the changes of resistance in the different temperature ranges. And next, this is the typical MSM structure characteristics. In the reverse bias and forward bias, basically you can say this is back-to-back PN diode, and that's why we are getting the same characteristics, bi-directional and symmetrical. And this is the changes of Schottky barrier height in accordance with the acetone concentrations at different temperatures. And then next, this is the transient response analysis in different temperatures with different acetone concentrations. We have measured the temperature ranges from 100 degrees Celsius to 250 degrees Celsius, and the acetone concentration was taken from 100 ppm to 1000 ppm. So from that transient analysis curve, we have measured the response magnitude, which is showing the conventional nature, and from here we can get the optimum temperature. You can see it is showing the best result at 150 degrees Celsius, and also we have calculated the response time and recovery time. This is also showing the good performance. And next, we have measured the selectivity study with different interfering species like ethanol, butanol, toluene, benzene, hexane, etc. And this is showing that it is very much selective towards acetone. And then we have measured the stability study for different hours, and it is showing almost stable results. So we can say it is very much stable sensors. And for the repeatability study, we have measured at 150 degrees Celsius and for 1000 ppm acetone vapors. So it is showing almost same results at the different conditions. And at the next, we have studied the hysteresis curve, which is showing whenever we are increasing the acetone vapor concentration as well as decreasing the concentration, it is showing almost same results whenever we are decreasing or increasing the concentrations. And the temperature was fixed at 150 degrees Celsius at the optimum temperature. And this is the sensing mechanism. Whenever a acetone molecule comes, and as you know, it is a dipole moment is 2.9 dy. So whenever a molecule comes, it will interact with the surface, and from the surface states it will immediately change the carrier concentration at the hetero interface, and these are some surface adsorbed oxygen states, and how these will react with the acetone molecules, and ultimately this will donate the electrons to the surface, which will reflected in the results by changing the current. And now this is the kinetic analysis. This is the IT versus O with time curve. So IT is the any current value at any given temperature, and I0 is the equivalent current value. So it is showing the exponential nature, and now by using the adsorption and desorption equations, we are getting the adsorption characteristics of the acetone at the surface of AlGaN. So these are the equations. By using the equations, these are the adsorption equations, and in the next slide, this is the desorption equations. By changing the reaction rates and all these things, we are getting very good adsorption and desorption characteristics. And by plotting the RNS plot, at last we are getting the adsorption energy and desorption energy for the acetone adsorption desorption at the solid surface of AlGaN. And these are the sensing properties we are getting from the result, which is showing that very good baseline recovery is there, along with the very good sensing performance at 150 degrees Celsius temperature. So this can be very useful in different applications along with biomedical applications. So to summarize this, So we are getting a very good acetone sensing property of AlGaN GaN sensor at 150 degrees Celsius, along with its reaction rates and all these energy absorption and desorption at 150 degrees Celsius. We are getting very good results. So these are the future scope. We can optimize more for different structural variations, and studies of different passivation scheme can be applied to this structure, and sensor selectivity study can be further forwarded for different organic vapors, and also this can be a very good useful for RF and baseband, which is useful for Internet of Things. And these are my references. I would like to acknowledge SCRB, Government of India, High Performance Device Laboratory, HTDC, IIT Kharagpur, Central Research Facility, IIT Kharagpur, and Nanothin Film Labs and Solid State Gas Sensor Devices Laboratory, ETC, IST Shibpur, and Center for Design and Fabrication for Electronic Devices, IIT Mandi. Thank you.